Welcome back, friends. So we are in seeing the properties of Fourier series coefficients, that is Cn. So in that, the next property what we have to see is conjugate property. What is conjugate property? What is conjugate property? Okay, listen here. If x of t signal having Fourier series coefficient Cn, then what is the Fourier series coefficient of x conjugate of x of t having Fourier series coefficient Cn, then what is the Fourier series coefficient of x conjugate of t is nothing but c minus n conjugate. C minus n conjugate. From this, we are having some symmetry properties. What are the symmetry properties? Let's say symmetry property. First one, let's say if x of t is real and even, then what is the nature of Cn? That means if x of t is real and even, then what is the nature of Cn? Now we know that if x of t is real or any number is real number, then how can we test whether it is a real number or not, or whether it is a real signal or not? So if you take the conjugate of that, then if it is going to give you the same, then it is called as real. So x of t is real means, so it has to satisfy x of t conjugate is equal to x of t. So real, x of t is real. If it is real, it has to satisfy x conjugate of t is equal to x of t. Then if I apply Fourier series coefficient on both sides, we know x conjugate of t having Fourier series coefficient c minus n conjugate is equal to Cn. So this property we already know. Whenever x of t is real, Cn is equal to c minus n conjugate. This is what we already know. Now, if x of t is even, if it is a even function, then it has to satisfy x of minus t is equal to x of t. If I apply Fourier series coefficient on both sides, then x of minus t having Fourier series coefficient c minus n and is equal to Cn, By combining all the properties, let's say Cn is equal to c minus n conjugate is equal to c minus n, or we can write Cn is equal to c minus n conjugate. So by seeing this, what we can say? So let's say what we can say: Cn and c minus n both are same. So from this, Cn and c minus n both are same. What is that? It is nothing but even function. Cn is equal to c minus n conjugate. So c minus n conjugate is equal to Cn, right? Or we can say, what is c minus n? C minus n is equal to Cn conjugate. So this is also equal to Cn conjugate. C minus n is equal to Cn conjugate. Okay, I am writing it 9. C minus n, and c minus n is equal to Cn conjugate. So from this, what we can decide? Cn is equal to c minus n, that means even. Cn is equal to Cn conjugate. So that means it is a real. So Cn is also real and even. Real and even. So what I am trying to say is, if x of t is real and even, then definitely Cn is also real and even. So like that, we are having, suppose if it is real and odd, suppose if it is imaginary and even, imaginary and odd. So for that we can derive, but I am just giving you a table here. So x of t and Cn, what is the nature? X of t nature, and what is the nature of Cn? If x of t is real and even, directly I am writing like this code word, real and even. Then Cn is also real and even. If it is real and odd, then it is imaginary and odd. If it is imaginary and even, then it is imaginary and even. If it is imaginary and odd, then it is real and odd. So these are the properties you have to remember. So it is easy to remember. Whenever you say even, even, the property does not change. Why? Real even is same as real even. Imaginary even is same as imaginary even. Next, odd. But real becomes imaginary, imaginary becomes real. This is the things you have to remember. So if it is even, so the property does not change. Real becomes real only, imaginary is imaginary. But if it is odd, real becomes imaginary, imaginary becomes real. So if you know x of the nature, you can directly say Cn nature. So by remembering this table. And what if x of t is a real and neither even nor odd? Real and neither even nor odd. Then a Cn is a complex. Cn is complex and exhibit and conjugate symmetry. Complex and conjugate symmetry. It exhibit conjugate symmetry. These are the things you have to remember. Clear? Take it. Property. Differentiation property. Differentiation property. What is the differentiation property saying that? If x of t having Fourier series coefficient Cn, then dx of t by dt. You might know in Laplace transform, if you could remember, x of t is having x of s Laplace transform. Then dx of t by dt having Laplace transform s into x of s. S into x of s. So where s can be replaced with j omega. Here we have to replace with jn omega naught. That omega is a continuous frequency, n omega naught is a discrete frequency. So we have to write jn omega naught multiplied with Cn. Jn omega naught multiplied with Cn. Suppose if I do differentiation m times dt power m, then we have to multiply jn omega naught m times. That means jn omega naught whole power m Cn. Whole power m Cn. So this is what we have to write. Clear? Differentiation property. So this differentiation property is very useful. Suppose let's say a question, how we can tackle that question. Let's say question number 16. It will be like this. Zero, 1, 2, 3, 4, like that. This is x of t. For this, options Cn, Fourier series coefficient, Cn is proportional to 1 by n. Option B, Cn is proportional to 1 by n square. Option C, Cn is proportional to 1 by n cube. Option D, Cn is proportional to 1 by n power 4. Which option is going to be correct? Which option is going to be correct? Okay. Now we can use a differentiation property here. What is differentiation property? dx of t by dt. Let's call it is y of t. Let's call it is y of t is equal to 0, 1, 2, 3, 4. So let's call it is minus 1, minus 2. If I differentiate this one, so we have to write the slope here, that is a. We have to write minus a here, plus a minus a, like that it will go. Okay, a minus a. Now it is having Cn, which is definitely Cn. Suppose let's say y of t having Fourier series coefficient dn. What is dn actually? Minus j. Actually this is actually what we can write, an minus bn by an minus j bn by 2. So in that an value is equal to 0 because it is an odd function. Then what is the bn value, which is nothing but 4a by n pi. So it is minus j 4a by n pi by 2 by 2. 2 to get cancelled finally. Okay, I am writing everything here so that you cannot get confused. 0 minus j 4a by n pi by 2. So it is going to be minus j 2a by n pi. Next, y of t having dn. So what is dn actually? Suppose x of t is having cn. This is j omega cn. So j omega cn, jn omega naught, jn omega naught cn is equal to minus j 2a by n pi. j get cancelled, then cn is equal to 2a by n square omega naught pi. So here cn is proportional to n square, 1 by n square. Cn is proportional to 1 by n square. It is as simple as that. So for a square wave, Cn is proportional to 1 by n. Actually, for square wave, it is proportional to 1 by n. Triangular wave, so we have to differentiate it one time. So we have to divide with again n. So it is going to be 1 by n square. Okay, like that we have to say. Okay, take it. If I take a impulse train, what is the impulse train? How it look like with respect to t? At 0, we are having one impulse function, let's say amplitude a. At t, we are having another impulse function. At 2t, another impulse function, and so on. At minus t, at minus 2t. This is the impulse train what we are having. Now for this we have to calculate what is the Fourier series coefficient Cn. So Cn, directly we are having the formula, which is 1 by t integration over a period. Let's take minus t by 2 to plus t by 2. X of t e power minus jn omega naught t dt. So minus t by 2 to plus t by 2, minus t by 2 to plus t by 2. What we are having? One impulse function, which is nothing but a delta t. So 1 by t integration minus t by 2 to t by 2 a delta t e power minus jn omega naught t dt. So delta t is multiplied with this one. So any signal multiplied with delta t, then t has to be replaced with 0. If t is replaced with 0, this value will become 1. So finally we are getting a delta t. So what is the area under a delta t? That is nothing but a only. So finally we are going to get a by t. So Cn is equal to a by t. This is the Fourier series coefficient of impulse train. Okay. Next. So till now we have considered square waves which are having 50% duty cycle. What do you mean by 50% duty cycle? The on time and off time are same. What if I take a square wave without 50% duty cycle? How to find out Cn value? That is much simpler. Let's see. Square wave without 50% duty cycle. Without 50% duty cycle. Let's see. Minus a 0 a minus t by 2 plus t by 2 a. Okay. So here the on time and off time not same. So it is not a 50% duty cycle. For this we have to calculate what is the Fourier series coefficient. I will directly go with the formula. What is that? Cn is equal to 1 by t integral minus t by 2 to t by 2 x of t e power minus jn omega naught t dt. This is the direct formula. So if I apply directly this formula, this is 1 by t. So integration I can take only from minus a to a, because minus t by 2 minus a, there is no signal. So minus a to a, what is x of t value? A e power minus jn omega naught t dt. A by t, a by t, e power minus jn omega naught t, e power minus jn omega naught t divided by minus jn omega naught. Here we have to apply the limits are minus a to plus a. Then what will happen? That is equal to a by t. Because of the minus sign, I will apply lower limit first. A by t into jn omega naught. If I apply lower limit, this is going to be e power jn omega naught a minus e power minus jn omega naught a. Bring this j into this and multiply and divide with the 2. Then it is going to be 2a by n t omega naught. This is 2j. So sine n omega naught a. Sine n omega naught a. What is omega naught value? Actually 2 pi by t, right? 2a by n t 2 pi by t. T get cancelled. Sine n omega naught a. Or we can write omega value is also 2 pi by t into a. So next t get cancelled, 2 get cancelled, a by n pi sine n 2 pi n a by t. So this is what the Fourier series coefficient Cn. So we can directly say this is the value. Okay. Suppose if any question comes, mostly the question is not going to be in the without 50% duty cycle. It's mostly 50% duty cycle only questions will be asked. If anything comes, then you can understand how to find out the Cn value. Now, if you want, you can remember directly. So it is better to remember n omega naught a only. It is easy to remember in that way. Sine n omega naught a. Clear? Take it. Next property, time scaling property. time scaling property. What is this property saying? That if x of t is having Fourier series coefficient Cn, then x of alpha t is also having the same Fourier series coefficient. How it is going to be, sir? But there is a small difference here. What is the difference is, here if you assume fundamental frequency is equal to omega naught, fundamental frequency is equal to omega naught. Here the fundamental frequency will become alpha omega naught. How it is going to be possible? Let's, you can understand. Just I will take x of t expression, summation n is equal to minus infinity to infinity Cn e power jn omega naught, jn omega naught. Then what is x of alpha t? That means t is replaced with alpha t. So n is equal to minus infinity to infinity Cn e power jn omega naught alpha t. Take this alpha here, summation n is equal to minus infinity to infinity Cn e power jn alpha omega naught t. So if you observe carefully, here e power jn omega naught t, the coefficient is Cn, e power jn alpha omega naught t. So for this also the coefficient is Cn, but only the thing is, here the fundamental frequency is omega naught, here the fundamental frequency is alpha omega naught. So I can simply say, so don't change that Cn values, keep the Cn value as it is, but only thing you have to change is fundamental frequency, because from this wave to this wave the only change we can observe is fundamental frequency. Clear? Take it. Question number 17. For a real periodic signal, for a real periodic signal, the exponential Fourier series coefficient C3 is equal to 3 plus J5, 3 plus J5. Then C minus 3 is equal to dash. Options: 5 plus J3, option B, minus 3 minus J5, option C, minus 5 plus J3, 3 minus J5, 3 minus J5. Okay, so listen carefully. This is the Fourier series coefficient C3, then we have to calculate C minus 3. So the clue they have given is a real periodic signal. I told you, if x of t is real, then we are having a relation between Cn and C minus n. What is that? C minus n is equal to Cn conjugate. C minus n is equal to Cn conjugate. So they want to find out C minus 3 now. That is nothing but C3 conjugate, that is 3 plus J5 conjugate, which is 3 minus J5. 3 minus J5. Option D. Clear? Take it. Take one example question. The Fourier series coefficients of x of t is Cn. Obtain the Fourier series coefficient of First question. X of t minus t naught plus x of t plus t naught. What is the Fourier series coefficient of this one? Second one. X even part of t. And third question. I hope it is over. X real part of x of t. Real part of x of t. Fourth question. X of 3t minus 1. X of 3t minus 1. So for x of t we know Cn. Then what is the Fourier series coefficients for these kind of waveforms? Okay. Now listen. I can directly write. What is the Fourier series coefficient of x of t minus t naught? That is Cn e power minus Jn omega naught t naught plus x of t plus t naught, that is Cn e power Jn omega naught t naught. So if I take Cn common out, this is e power Jn omega naught t naught plus e power minus Jn omega naught t naught. Suppose if you multiply with 2 and divide with 2, that is going to be 2Cn cos n omega naught t naught. Now coming to this one, x even part of t. Usually what we can write x even part of t, that is x of t plus x of minus t by 2. For this we require to know what is the Fourier series coefficient. So x of t is having Cn is the Fourier series coefficient and x of minus t is having C minus n as the Fourier series coefficient by 2. So this is the Fourier series coefficient if it is a even part. Next, real part of x of t. You might know, let's say, suppose z a plus jb, z conjugate a minus jb. Suppose if I want to find out real part of z, which is a, then how it is going to be z plus z conjugate by 2. Z plus z conjugate by 2. So in the similar manner, this is also can be written as x of t plus x of t conjugate divided by 2. In this way we can write. For this we have to calculate what is the Fourier series coefficient. For x of t, this is Cn. For x conjugate of t, C minus n conjugate by 2. Clear. Next, x of 3t minus 1. So whenever there are multiple operations are given, then go for property by one. What do you mean by that? Let's see. First what we know. Start from what we know. X of t is having Fourier series coefficient Cn. Clear. Then x of t minus 1. So which is similar to shifting property x of t minus t naught, only the change is t naught value is equal to 1. Then Cn e power minus Jn omega naught t naught value is equal to 1. Next, x of 3t minus 1. So whenever t is replaced with 3t, then we have to apply the scaling property. Just now we have seen scaling property, nothing is going to change, only the fundamental frequency is going to change. So Cn e power minus Jn omega naught dash. What is the omega naught dash value? That is nothing but 3 omega naught. Omega naught dash, that is the fundamental frequency, that is 3 omega naught. This is the only thing it is going to change. Clear? Take it. You are going to see this theorem even in Fourier transform, DFT, DTFT. So everywhere this theorem will be continued. Okay. So let's see. Whenever I say Parseval's theorem, it may talk regarding energy or power. So but in our case, that is a Fourier series, it's always about the power, because x of t is a periodic signal. Every periodic signal is nothing but a power signal. So in general, how we can calculate power of x of t? Power of x of t, if you know x of t, then directly we can use the formula 1 by t integration over a period mod x of t whole square dt. So this is the power formula if it is a periodic signal. If it is a periodic signal. So this is the formula what we can use. Now, what the Parshall's theorem is saying that, yeah, you know x of t, you can find out by using this formula. But what if you know Cn? Can you calculate the power? Yes. Why? I already told you, frequency domain representation and time domain representation is going to give you the same information. So that means from the frequency domain representation, which is nothing but Cn, that is nothing but frequency domain. So Cn is also going to be used to calculate the power. How? So the Parshall's theorem is saying that simply this is equal to summation n is equal to minus infinity to infinity mod Cn square. Mod Cn square. This can be expanded like this also. Here minus infinity to infinity, everything is going to be repeat. Why? Mod Cn and mod C minus n both are same. Only the thing is mod C naught, which is existing only one time, plus 2 into summation n is equal to 1 to infinity mod Cn square. So this is the way we can directly write the formula. So power of x of t. This is what the Parshall's theorem. You have to remember. Clear? Take it. Okay. Let's solve one question. Example. Well-known waveform I am taking. So this is the x of t they have given. In that, the first question is find power of x of t. Find power of x of t. Second question is find power of x of t up to third harmonic. Up to third harmonic. This is the question. Okay. We know what is x of t, so we can write it. That's a different story. Otherwise, we can directly find out, because it is a periodic signal, I can directly find out what is the power. Power is equal to x RMS square. X RMS square. So what is the x RMS value for a periodic wave? Root of amplitude 1, and here duration is 1. 1 square into 1 plus next amplitude is 0 for duration 1. 0 square into 1 by total period 1 plus 1 whole square. So this is the formula. So for directly this is going to give you 1 by 2, 0.5 watts. 0.5 watts. So this is the power of x of t. So directly we can use the direct formula x RMS square, we can find it out. But here, coming to this question, find power of x of t up to third harmonic. Here the trick is, so I cannot use x of t directly because they are asking about harmonics. That means they are the frequencies. Now what we have to see, let's say power up to third harmonic. First of all, what is Cn value for this? Cn is equal to 0 minus jbn, that is nothing but 2 by n pi by 2. So minus j 1 by n pi. minus j 1 by n pi. So this is the formula for Cn. For this way, power up to third harmonic, then it is summation, or we can say mod C naught square plus summation 2 into summation n is equal to 1 to 3. Why? Up to third harmonic only. So mod Cn square. But that too, it is only for odd values of n. Now we can expand this formula again. Mod C naught square plus 2 into, if n is equal to 1, this is mod C1 square. If n is equal to 2, that value is 0 because it is existing only for odd values of n. C2 is equal to 0. Then we have to go for C3 whole square. So this is the formula what we got. Now what is the C0 value? C0 is equal to A0, which is equal to 1 by 2. So 1 by 2 whole square plus 2 into, what is C1? If n is equal to 1, 1 by pi. So magnitude is 1 by pi square plus 1 by 3 pi square. So if you calculate this one, you are going to get 0.475 watts. So this is the final power up to third harmonic. Now here one very interesting point what I want to discuss is, if you observe total power, which is 0.5 watts, but if I calculate the power up to third harmonic, that is equal to 0.475 watts. So from this I can conclude that even up to third harmonic we are having almost all 95% of the power. That means, so if you consider lower harmonics up to third harmonic only and leaving every harmonic after 3, still you are containing 95% of power. That means lower frequency components having the large power compared to the high frequency components. In this regard, we can neglect high frequency components. That's why sometimes we are having the Fourier series only for certain what we can say sine terms or cosine terms, because after that the power is negligible. I hope you understood. So high frequency components are negligible because the power carried by them is very less compared to the low frequency components. Clear? Take it. And this is the last topic in the Fourier series, and next we are going to start with the Fourier transform. Okay, take it.